Hello everyone, today let's take a look at QP159, a pretty basic question about general continuous distributions. So we have this density function here, f of t, it's equal to k times 2 minus t, where t is between 0 and 2, and in part A we need to find the value of k that makes f of t a valid PDF. So essentially if you plot out this density function right here, you see we intercept the y-axis at the point 2k, because when t is equal to 0, we just have 2k here in our density function, and the density function is basically going to be decreasing at a rate of t times k, right? So t is going between 0 and 2 as well. At this point right here, we have t equal to 0, and at this point right here where it crosses the x-axis, we're going to have t equal to 2, because when we plug t equals 2 into here, we get 0, because we're going to have 2 minus 2, obviously, right? Now, in the continuous case, you basically represent probability as area. For instance, the probability that the battery lifetime is equal to exactly 1 is going to be 0, because that has no area. Any singular point is going to have 0 probability, right? Because it's a continuous random variable. So the probability it's exactly equal to 1 is going to be infinitely small, right? We're going to have instead probably 1.00000 out to infinity, right? Maybe 1.0001, right? It's impossible to be a specific value in the continuous case. However, if you define some type of range of values, so for instance, maybe everything between 1 and 1.5, right? Well, then that gives us some actual area, right? We can calculate the area right here, and that will be the probability that the flashlight light lasts somewhere between 1 and 1.5. So because t goes from 0 to 2, we know that the entire area under this basically function right here has to be equal to 1 in order to be a valid probability distribution, right? All of this area has to be equal to 1. So by imposing that constraint, this area here has to be equal to 1. We can basically just solve for k. So now you could do this in two ways. Since our density function is so simple, right? It's just a straight line. We could just calculate the area of this triangle right here, or we could use an integral either way. First, by calculating the area of a triangle, we know that the base of this triangle is going to have length 2, and the height of it has basically length 2k. So 2 times 2k, and then we have to divide it by 2, right? That's obviously the area of a triangle. That's going to give us 2 times k. However, because we need this area to be equal to 1, we know that basically we can solve for k now, and k is going to equal 1/2. Or alternatively, you could solve for this area by integrating. If you had a more complicated distribution function, well then this is what you do, right? You basically integrate for over all the possible values that t can take. So between 0 and 2 in this case, basically the density right here, which is just going to be 2k minus basically kt when we expand out this k, and then that's going to be with respect to t. And then evaluating this integral right here, the antiderivative of this part right here will just be 2kt evaluated from 2 to 0. When we do that, we're just going to get 4k for that first part, and now for the second part we're going to have, well, the antiderivative of negative kt is just going to be negative k on 2 times t squared, right? And that's going to be evaluated from 2 to 0. When we plug in 2, we get a 4 here, and then when we plug in 0, we get 0, so that's going to be irrelevant. So we just have basically 4k minus 4k on 2, which is just equal to 4k on 2, which again is just equal to 2k. When you enforce that that has to be equal to 1 in order for it to be a valid PDF, again, you get the fact that k is equal to 1/2. So that's the final answer for part A, k equals 1/2. So now in part B, it asks us what is the probability that a battery lasts more than 1.5 hours? So I guess t here represents hours. But now that we know what k is, basically our density function is just going to be, if we plug in k, 1/2 times 2 minus t, like so, which is just equals to 1 minus 1/2 times t. So essentially this intercept right here is just going to be 1, and we're going to have a slope here of negative 1/2, right? And now we want to calculate the probability that t is greater than 1.5. So if I have 1.5 right here, we basically just want to calculate this area. That's going to give us the probability that t is greater than 1.5. Because the PDF is so simple, we can calculate this area pretty easily, right? It's just the area of a triangle where this side length right here is 1/2, right? Just 2 minus 1.5. And then this height right here, you can calculate just by plugging in 1.5 into our density function. So 1.5 is equal to 3/2. If I plug that in right here, right, I just get 3/4 right here, and then I get 1 minus 3/4, which is just equal to 1/4. So we know the height right here is 1/4. We have this side length of 1/2. We know how to calculate the area of a triangle. It's going to be 1/2 times 1/4 in this case divided by 2. That's just going to be 1/8 divided by 2, which is just equal to 1/16. So that's the final answer for part B. So again, the density function right here, sorry to get rid of it, it's it's just going to be 1 minus 1/2 t. We know that the probability that t is greater than 1.5, which is what we calculated in part B, we just found that that was equal to 1/16 just by calculating the area under this curve between 1.5 and 2. So there's your final answer for part B. Now in part C, we just want to calculate the expected value of the length of this battery lasting. So we need to find the expected value of t. The expected value in the continuous case, we're basically just going to integrate over all the possible values that t can take. In this case, it's between 0 and 2. And then we're going to take the length, right, t, and we're going to multiply that by the density of that length occurring, right? So f of t times t and then dt. So essentially what we're doing here is we're basically looking at every single point between 0 and 2. Those are all the possible values that t can take. And then we are essentially taking the density at a specific point and multiplying that by basically the length at that point. So we're going to have some t value here and some density, and we're going to multiply them together. And that's for every single value of t between 0 and 2. That's how you calculate the expected value in the continuous case. So in our case, the density function is going to be 1 minus 1/2 t. So we multiply t by 1 minus 1/2 t like so, and then we integrate with respect to t. So now to evaluate this integral, we can split it into 2 by distributing that t inside here, right? So our first integral will be from 0 to 2 of t dt, and then our second one, we're going to have negative, basically the integral from 0 to 2 of 1/2 t squared dt. Now we can just solve this. Now the antiderivative of t is just going to be t squared divided by 2. We're going to evaluate that from 2 to 0. When we do so, we're just going to get 4 on 2, which is equal to 2. So that integral is equal to 2. And then for our second integral right here, first of all, what we can do is pull out this 1/2 because it's a constant with respect to what we're integrating over, right? And now we just need to calculate basically the integral of t squared. We know that the antiderivative of t squared is just going to be t cubed divided by 3. We evaluate that from 2 to 0. The only thing that's going to matter is the 2. When we plug in 2, we get 8 on top, so this is going to be 8/3. So that's our final answer. It's going to be 2 minus 1/2 times 8/3. 1/2 times 8/3, that's just going to be 4/3. So 2 minus 4/3. So 2 is also known as 6/3, right, to get it over a common denominator. 6/3 minus 4/3 is going to be 2/3. So that is the expected value of t. It's going to be 2/3. That makes sense because basically 2/3 is somewhere over here, and you can see that the smaller values have higher density, right? So they should be more likely. So 2/3 makes sense. And then finally in part D, the question is asking us, what is the probability that the battery lasts more than, what is the probability the battery lasts more than 1 hour, or more than 1.5 hours, given that it's already lasted more than 1 hour. So the probability that t is greater than 1.5, given that t is basically greater than 1, right? So definition of conditional probability, this is just going to be equal to the probability that t is greater than 1.5 and t is greater than 1. But if t is greater than 1, then the only thing that we care about is t being greater than 1.5. So the probability that t is greater than 1.5 divided by the probability that t is greater than 1. Again, just the definition of conditional probability. Now in part B, we already calculated the probability that t was greater than 1.5, right? We got 1/16. So now we just need to calculate the probability that t is greater than 1. So let's go up to our diagram right here and let's look at the point 1 and let's see what we get. So the probability that t is greater than 1 is just going to be all of this area between 1 and 2, right? Which is just going to be another triangle. We know how to calculate the area of a triangle. This side length right here is going to be 2 minus 1, which is equal to 1. And then the height of this triangle right here is when we plug in 1 into our density function. When we do that, we're going to get 1 minus 1/2 here, which is just equal to 1/2. So this will be equal to 1/2. Now when we multiply 1/2 times 1 and we divide that by 2, we just get 1/2 divided by 2, which is equal to 1/4. So that's the area of that little triangle right there. So the probability that t is greater than 1 is equal to 1/4. We already calculated the probability that t is greater than 1.5. That was 1/16. So 1/16 divided by 1/4, that's just going to be equal to 1/4, right? So that right there is our probability for D, the probability that t is greater than 1.5, given that t is greater than 1. So that solves every part of this question. You can see just a pretty simple continuous distribution question where we're just directly working with a PDF of a given distribution, and we're finding all of these properties, right? The expected value, conditional probability, right? Probability in general, stuff like that. So that's how you work with continuous distributions.